On December 27th, 2004, something 50,000 light years away shook Earth's upper atmosphere. Not a comet, not a nearby explosion, a dead star. For 1/5 of a second, it released more energy than our sun will produce in the next 250,000 years combined. Gamma ray detectors across Earth overloaded almost instantly. Some scientists initially thought the instruments had failed. Before astronomers could fully process what had happened, the event was already over. And that object is only one of the terrifying places we know exists in the universe. There is a region of space so empty that if you stood at its center, you would see almost nothing in any direction. No nearby galaxies, no stars, almost no light at all. There is an object so massive that light itself takes more than 2 days just to cross the darkness around it. There is a hidden gravitational force pulling the Milky Way and hundreds of thousands of other galaxies toward a single point in space we still cannot clearly see. There are places where gravity slows time itself, where empty space becomes hotter than the surface of the sun, and where physics produces equations so broken they return the answer infinity. And none of these places exist at the edge of the universe. Several are disturbingly close. Every location in this video is real, observed, measured, published in peer-reviewed science, and together they reveal something unsettling about the universe we actually live in. If this kind of content helps you unwind at night, consider subscribing. We put out new space documentaries regularly, and having you here means a lot. The story begins with the dead star that briefly disturbed Earth's atmosphere from the other side of the galaxy. If you step outside on a clear night and look upward, the sky appears crowded. Thousands of stars seem scattered across a dark ceiling, close enough to belong to the same immediate landscape. But almost everything your eyes can see exists inside an extremely small neighborhood of space. Every visible star lies within roughly 4,000 light years of Earth, a distance that sounds immense until you compare it with the Milky Way itself, which stretches across about 100,000 light years, and the Milky Way is only one galaxy among hundreds of billions. The scale hides inside the silence. A single light year is the distance light travels in 1 year, moving at 299,792 kilometers every second. In that time, light crosses approximately 9.46 trillion kilometers. The nearest star beyond our Sun, Proxima Centauri, sits 4.24 light years away. The places we are moving toward tonight begin around 18,000 light years distant and extend outward across billions of light years into regions where even light requires ages to arrive. What makes these places frightening changes as the distances grow. Some are terrifying because of violence, objects collapsing, exploding, or releasing impossible amounts of energy in fractions of seconds. Others disturb us through emptiness, through regions so vast and hollow that familiar ideas about structure begin to fail. Some challenge physics itself, forcing equations toward infinities that scientists recognize as warning signs, places where current theories stop working properly. And then there are locations whose implications stretch into the future, revealing where the universe may ultimately be heading long after every living thing on Earth is gone. Yet no human being has ever visited any of them. Everything we know arrives indirectly. We study the universe through messengers crossing enormous distances. Visible light is only one of those messengers, and not even the most important. Radio telescopes collect wavelengths invisible to human eyes, revealing cold gas clouds, pulsars, and distant galaxies hidden behind dust. X-ray observatories orbit above Earth's atmosphere because our atmosphere blocks X-rays completely, protecting life below while also concealing violent cosmic events from ground telescopes. Gravitational wave detectors work differently still. They measure distortions in space itself, changes smaller than the width of a proton, passing through instruments several kilometers long. Most discoveries did not happen because astronomers searched for something terrifying. Many emerged accidentally, buried inside unrelated observations, unnoticed for years. Signals crossed the galaxy, reached Earth, and quietly sat inside archived data until someone looked closely enough to realize what had arrived. And one of the strangest examples was comparatively nearby, hidden inside our own galaxy, only 18,000 light years away, where an object no larger than a city briefly released enough energy to overwhelm gamma ray detectors across Earth all at once. Deep inside the wreckage of certain dead stars, gravity compresses matter beyond anything familiar. A mountain of mass collapses into a sphere, barely 20 kilometers wide. Protons and electrons are crushed together until they become neutrons, producing what astronomers call a neutron star, an object so dense that ordinary language begins to lose accuracy around it. But a magnetar is something worse. Its magnetic field reaches around 1 quadrillion times stronger than Earth's. In scientific units, roughly 10 to the power of 15 Gauss. Nothing naturally occurring in the known universe possesses a stronger magnetic field. Not planets, not ordinary stars, not even most black holes. The effects become lethal long before you ever reach the surface. At a distance of roughly 1,000 kilometers, the magnetic field alone would begin disrupting the iron atoms inside hemoglobin, the molecule carrying oxygen through human blood. The body would fail before heat or radiation even mattered. At around 160,000 kilometers, still less than halfway to the moon, the field could erase magnetic storage across Earth simultaneously. Hard drives would fail, credit cards would blank, MRI machines would shut down permanently, and the object causing this destruction would still appear only as a distant point. On December 27th, 2004, one magnetar briefly announced itself across the galaxy. The object was SGR 1806 20, located approximately 50,000 light years from Earth, near the constellation Sagittarius. For 2/10 of a second, it released an enormous pulse of gamma rays and X rays. The burst crossed the entire Milky Way and still carried enough energy to ionize part of Earth's upper atmosphere upon arrival. The energy output exceeded what our Sun will produce across 250,000 years. Satellites detected it instantly. Our HEC lost normal function for a moment. Integral saturated completely. The Rossi X-ray Timing Explorer recorded overload effects that initially resembled instrument failure rather than a real astrophysical event. Scientists checking the incoming data first suspected something had gone wrong with the detectors themselves, but the signal was real. A magnetar's surface gravity reaches roughly 200 billion times stronger than Earth's. If you dropped a marshmallow from 1 meter above the surface, it would strike with energy comparable to a nuclear weapon. Matter there no longer behaves according to human intuition. Atoms distort, electron clouds compress. Space around the star becomes physically hostile to stable structures. The 2004 flare likely began with a starquake, a magnetar's crust, a thin, rigid shell surrounding the neutron matter beneath, can fracture under magnetic stress. The shift may have measured only about 1 centimeter, yet that tiny rupture released energy equivalent to roughly 10,000 years of solar output almost instantly. Only around 30 confirmed magnetars currently exist within the Milky Way, but their active lifetimes remain short, roughly 10,000 years before the magnetic field decays and the violence fades. That means countless others may already be gone, cooled into quieter neutron stars long before human beings ever learned to look upward. For a few thousandths of a second, a radio signal crossed the Milky Way and reached Earth on April 28th, 2020. It arrived from a magnetar called SGR 1935 plus 2154, located roughly 30,000 light years away in the constellation Vulpecula. The pulse was brief enough to vanish almost immediately, but what mattered was not its duration, it was what the signal resembled. Astronomers recognized it as a fast radio burst, usually shortened to FRB, a sudden flash of radio energy lasting only milliseconds. Until that moment, every confirmed FRB had originated far beyond the Milky Way, crossing billions of light years before detection. Their distances implied extraordinary power. Entire observatories had spent years trying to determine what kind of object could release so much energy so quickly. Then one happened inside our own galaxy. The burst from SGR 1935 plus 2154 was weaker than the giant extragalactic FRBs by about a factor of 1 million. Yet it carried the same essential structure, the same sharp radio signature, compressed into milliseconds. For the first time, astronomers had direct evidence connecting magnetars to at least some fast radio bursts. The mystery suddenly narrowed. But the story itself had begun years earlier, hidden inside old data. In 2007, astronomer Duncan Lorimer and his student David Narkovich were analyzing archival recordings from the Parkes Radio Telescope in Australia when they found an unusual signal buried in observations from 2001. It lasted less than 5 milliseconds. Different radio frequencies arrived at slightly different times, a delay caused by the signal crossing enormous amounts of intergalactic matter before reaching Earth. The burst had traveled for billions of years, and then it sat unnoticed on a hard drive for 6 more. Since then, observatories around the world have identified hundreds of FRBs. Most appear once and never repeat. Others behave differently. FRB 2012 1102A, traced to a dwarf galaxy approximately 3 billion light years away, produced 1,652 detected bursts across just 47 days during observations by China's FAST telescope in 2021. No single explanation fits every case cleanly. A typical non repeating FRB releases, within milliseconds, roughly the same energy our sun emits across 3 full days. Yet the source region may only span the size of a city. The physical compression involved becomes difficult to picture. Matter magnetic fields and radiation interact under conditions impossible to reproduce fully on Earth. But these bursts also became tools as FRB signals travel through space. Lower radio frequencies slow slightly more than higher ones. Astronomers call this dispersion. By measuring the delay precisely, researchers can calculate how much diffuse matter the signal crossed between galaxies. This helps solve a long standing cosmological problem concerning missing ordinary matter, the atoms predicted to exist but previously difficult to locate. And still, the repeating bursts resist simple models. Magnetars explain part of the phenomenon, perhaps even most of it, yet the full pattern remains unsettled, with no single theory accounting for every signal now cataloged across the sky. The death of a massive star happens with astonishing speed. For millions of years, the star holds itself upright through nuclear fusion, balancing gravity with outward pressure generated deep inside its core. Then the fuel runs out, fusion slows, pressure collapses, and within roughly 1/10 of a second, gravity wins completely. The core falls inward first. A star between about 8 and 20 solar masses compresses so violently that electrons and protons are forced together, forming neutrons packed almost shoulder to shoulder. What remains after the collapse is a neutron star, an object containing more mass than our Sun inside a sphere only about 20 kilometers across. Matter there no longer resembles ordinary matter. A single teaspoon of neutron star material would weigh around 10 million tons on Earth. The comparison barely helps. It is the mass of a mountain compressed smaller than a sugar cube. Atomic structure survives only in distorted form, crushed under pressures impossible to reproduce naturally anywhere else nearby in the universe. The collapse itself creates the explosion. As the core suddenly hardens, the outer layers of the dying star continue falling inward at roughly one quarter the speed of light. They strike the rigid neutron core and rebound outward catastrophically, producing a supernova bright enough to briefly outshine entire galaxies. The neutron star remains after the expanding debris fades, and the gravity remains extreme. Surface gravity reaches around 200 billion times stronger than Earth's. Escape velocity, the speed required to leave the surface permanently, approaches half the speed of light. A human body could never survive near such an object. Even chemistry struggles there. Some neutron stars spin rapidly after formation, conserving angular momentum from the original collapsing star. As they rotate, beams of radio energy sweep outward from their magnetic poles. If one beam crosses Earth repeatedly, astronomers detect regular pulses like a cosmic lighthouse. These objects became known as pulsars. The first pulsar appeared in data collected during 1967 by graduate student Jocelyn Bell Burnell in Cambridge. The pulses repeated so precisely that the signal was briefly labeled LGM1, standing for Little Green Men, because no known natural source behaved with such regular timing, but the mechanism proved entirely physical. One pulsar called PSRJ0437 4715 rotates 174 times every second while maintaining timing accuracy comparable to atomic clocks. Astronomers use pulsars like this to test general relativity itself, measuring tiny distortions in spacetime through changes in pulse arrival times. Yet the deepest layers remain uncertain. Inside a neutron star, pressure may become so intense that neutrons dissolve into their constituent quarks, producing quark gluon plasma, a state of matter last common during the first microseconds after the Big Bang. Particle accelerators on Earth have recreated this state briefly, but never at neutron star densities. In August 2017, two neutron stars merged 130 million light years away. The collision produced gravitational waves, gamma rays, and a kilonova, an explosion forging enormous quantities of heavy elements. In just 1.7 seconds, the merger created more gold than our sun will produce across its entire lifetime, scattering those atoms outward into future stars, planets, oceans, and eventually living bodies. There comes a point during stellar collapse when matter stops resisting, pressure fails, nuclear forces fail. The inward pull continues anyway, crushing the dying core beyond every stable state known in physics. If the collapsing mass exceeds roughly 3 times the mass of our Sun, no mechanism remains capable of holding gravity back. The collapse does not stop. What forms is a black hole, a region where space-time itself curves so steeply that escape becomes impossible. Escape velocity, the speed required to leave a gravitational field permanently, rises beyond the speed of light. Since nothing travels faster than light, nothing inside can ever return outward. The edge of this region is called the event horizon. It is not a solid shell, not a surface. There is nothing there you could physically touch. The event horizon is a boundary in geometry, the final distance at which return remains mathematically possible. Cross it once, and every future path through spacetime leads deeper inward. Even time changes near it. To a distant observer, a clock lowered toward the event horizon appears to slow gradually. Seconds stretch, motion fades. Just above the boundary, the clock seems frozen completely, trapped forever in its final visible instant. But from the falling object's perspective, time proceeds normally. The crossing happens without warning. Space itself becomes distorted. Near a stellar black hole, gravity affecting your feet would become dramatically stronger than gravity affecting your head. This tidal difference stretches objects vertically while compressing them horizontally, a process physicists informally call spaghettification. Long before reaching the event horizon, atoms would separate into thinner and thinner streams of particles. Yet black holes rarely appear directly. Most reveal themselves through interaction with nearby matter. One of the earliest confirmed examples, Cygnus X1, lies around 6,000 light-years away within the constellation Cygnus. It orbits a companion star while pulling gas away from it. That gas spirals inward into an accretion disk, a rotating structure heated to millions of degrees by friction and gravity, producing intense X-rays detectable from Earth. For years, even scientists argued over what it truly was. In 1974, Stephen Hawking made a famous wager with physicist Kip Thorne, betting Cygnus X, one would not ultimately prove to be a black hole. Hawking conceded the bet in 1990 after evidence became overwhelming. Then came the first image. In 2019, the Event Horizon Telescope linked observatories across Earth into a planet-sized instrument and captured the shadow of M87 star, a supermassive black hole 55 million light-years away containing about 6.5 billion solar masses. Around the darkness appeared a bright ring of superheated gas falling inward at relativistic speeds. But the central problem remained untouched. General relativity predicts that matter collapsing beyond the event horizon reaches a singularity, a point of effectively infinite density where the equations stop producing physically meaningful answers. Infinity inside physics is not a solution. It is evidence that the theory itself has failed somewhere, and another contradiction waits there too. Quantum mechanics states information can never truly disappear. Black holes appear to erase information permanently. Both ideas cannot remain fully correct simultaneously. Somewhere inside that contradiction, two of humanity's most successful theories stop agreeing with each other. Some objects overwhelm you not through violence, but through scale so extreme that comparison itself begins failing. TON 618 belongs to that category. It sits approximately 10.4 billion light-years from Earth in the constellation Canes Venatici, and the light reaching us tonight began its journey when the universe was only around 3.3 billion years old. We are not seeing it now. We are seeing a younger universe trying to build something impossible. TON 618 is classified as an ultramassive black hole. Its mass reaches approximately 66 billion times the mass of our Sun. The number is difficult enough to understand on its own, but the surrounding geometry makes it stranger still. The event horizon, the boundary beyond which return becomes impossible, extends outward roughly 1,300 astronomical units. One astronomical unit is the average distance between Earth and the Sun. That means TON 618's event horizon spans 1,300 times that distance. Our own solar system appears tiny beside it. From the Sun to Neptune's orbit measures only about 60 astronomical units. TON 6, 18's event horizon is roughly 21 times wider than the entire planetary system surrounding our star. If placed where the Sun currently sits, the boundary would extend far beyond the Kuiper belt into deep interstellar space. And this is only the edge. Light traveling across the full diameter of the event horizon would require approximately 2.5 days to complete the journey, but no photon crossing inward would ever emerge again. Even light, the fastest thing known in the universe, becomes trapped permanently once it falls too close. At peak activity, TON 618 radiated energy equivalent to roughly 140 trillion suns. It outshone entire galaxies, filled with hundreds of billions of stars. The source of that luminosity was not the black hole itself, but the surrounding accretion disk, gas heated by friction and gravity until it blazed across enormous distances. The black hole fed continuously. Matter spiraled inward at relativistic speeds, compressing and heating as it descended deeper into the gravitational well. The region surrounding TON 618 became what astronomers call a quasar, an intensely luminous galactic core powered by black hole accretion. But the existence of TON 618 creates another problem. Under standard models, black holes grow gradually by consuming gas, dust, stars, and merging with other black holes over immense spans of time. Yet the early universe may not have provided enough time to build an object reaching 66 billion solar masses, only 3 billion years after the Big Bang. The mathematics struggle to catch up. Some theories propose enormous seed black holes formed from the collapse of the universe's first giant stars. Others suggest periods of runaway growth far faster than previously expected. But recent observations from the James Webb Space Telescope complicated the situation further. Webb has begun identifying similarly massive black holes even earlier in cosmic history, appearing not as rare anomalies, but with unsettling frequency. And each discovery pushes the timeline backward again, forcing astronomers to confront the possibility that something fundamental about black hole formation in the early universe remains incomplete. Around certain supermassive black holes, matter does not fall inward cleanly. Gas spirals downward into an accretion disk, a rotating structure heated by friction, compression, and gravity until temperatures climb into millions of degrees. The material circles at relativistic speeds, meaning a substantial fraction of light speed, while magnetic fields twist violently through the disk like stretched wires under enormous tension. Some of that matter never reaches the black hole. Instead, magnetic forces redirect part of the inflowing gas outward through the poles, launching narrow jets into intergalactic space at up to 99.9% the speed of light. These are quasar jets, among the most energetic structures ever observed. They remain stable for astonishing distances. A quasar jet is not a beam of light. It is a stream of plasma, charged particles, and magnetic fields moving together across space while maintaining coherence for hundreds of thousands or even millions of light years. The jet from 3C 273, the first quasar identified in 1963, extends roughly 200,000 light years. That is longer than placing two Milky Ways side by side. And the particles inside continue moving almost unimpeded. Any planetary system passing near such a jet would face catastrophic radiation exposure. Atmospheres could erode away, ozone layers would collapse. Complex surface chemistry, the kind required for stable biological systems, would become extremely difficult to sustain under the continuous bombardment of high-energy particles. The violence becomes visible in nearby galaxies. Centaurus A, located approximately 13 million light-years away, is the nearest major radio galaxy to Earth. Its central black hole drives a jet powerful enough to heat surrounding gas clouds into temperatures of millions of degrees. The Chandra X-ray Observatory directly imaged the shock front produced where the jet plows into surrounding matter, creating a bow wave of superheated plasma spreading through intergalactic space. But some jets point almost directly toward us. Astronomers call these objects blazars. In a blazar, the jet aligns closely with Earth's line of sight, allowing us to look nearly straight into the outflow from a supermassive black hole. The brightness increases dramatically through relativistic effects, making the object appear even more energetic than it already is. One example, TXS 0506 plus 056, lies approximately 3.7 billion light-years away. In 2017, it became the first known source confirmed to emit both high-energy neutrinos and gamma rays simultaneously. Neutrinos are nearly massless particles capable of passing through entire planets almost without interaction. Detecting them from a blazar connected two previously separate forms of cosmic observation, and the motion itself can become deceptive. Some blazar jets appear to travel faster than light across the sky, a phenomenon called superluminal motion, but nothing actually breaks relativity. The illusion forms because material moving nearly toward Earth compresses the apparent time between emitted signals, making the jet seem to outrun light itself. The largest known example stretches even further. The jet emerging from galaxy B20026 plus 1, 2 spans approximately 1.5 million light-years, a single connected structure so immense that light would require over 1 million years merely to cross from one end to the other. For a few seconds, a single point in space can outshine almost everything else in the observable universe combined. Then the signal disappears completely, leaving only fading afterglow behind. These events are called gamma ray bursts, or GRBs, brief eruptions of radiation carrying more energy than our sun will emit across its entire 10 billion year lifetime. The release happens extraordinarily fast. Long gamma ray bursts usually last between 2 seconds and several minutes. They begin when massive stars collapse directly into black holes at the end of their lives. As the stellar core falls inward, twin jets punch through the dying star's outer layers at nearly the speed of light. If one jet points toward Earth, detectors across space register a violent pulse of gamma radiation. The beam narrows sharply. A long GRB does not radiate equally in every direction. The opening angle may span only a few degrees, meaning most bursts occurring inside the Milky Way would never intersect Earth at all. Survival depends heavily on orientation. We are protected largely by geometry rather than distance. Short gamma ray bursts emerge differently. These bursts last under 2 seconds and originate from neutron-star mergers, the same collisions responsible for forging gold and other heavy elements. But the gamma ray jet travels along a specific direction, while gravitational waves spread outward through space-time itself. Most kilonovae therefore remain invisible as GRBs unless Earth happens to lie within the narrow beam. When one does align properly, the effect becomes unmistakable. On October 9th, 2022, observatories detected GRB 221009, a quickly nicknamed the Boat, short for brightest of all time. The burst originated approximately 2.4 billion light-years away. Despite that enormous distance, It saturated instruments aboard nearly every gamma ray observatory simultaneously. Some detectors temporarily lost normal function because the incoming radiation proved too intense to measure cleanly. And it was not even nearby. A gamma ray burst directed toward Earth from within roughly 6,000 to 8,000 light years could strip away much of the ozone layer on the facing hemisphere within seconds. Ultraviolet radiation from the sun would then reach the surface largely unfiltered. The far side of the planet would remain shielded only temporarily until Earth's rotation exposed it as well. The possibility has shaped extinction research too. Some scientists investigating the Ordovician extinction, approximately 443 million years ago, proposed that a nearby GRB may have triggered severe atmospheric damage, contributing to the loss of around 85% of marine species. The hypothesis remains unconfirmed, but current evidence does not eliminate it, and the bursts reach across extraordinary spans of time. The most distant confirmed GRB traveled approximately 13.1 billion light years before reaching Earth. The star producing it died when the universe was less than 700 million years old, long before the Milky Way fully formed, long before the atoms making Earth's oceans or atmosphere had assembled into planets. The radiation crossed nearly the entire observable universe uninterrupted, and somewhere during that journey, life emerged on a small world orbiting an ordinary star, eventually building instruments sensitive enough to detect the final seconds of a collapsing sun that vanished billions of years before our planet existed at all. In 1981, astronomers were not searching for anything mysterious. Robert Kirshner and his colleagues were conducting a galaxy redshift survey, measuring how galaxies spread across a region of sky near the constellation Boötes. Redshift surveys work by tracking how light stretches as galaxies move away through cosmic expansion, allowing researchers to map large-scale structure across enormous distances. The data should have formed a pattern. Instead, one region appeared strangely empty. At first, the team suspected equipment problems, then processing errors, but repeated observations returned the same result again and again. A huge section of space contained far fewer galaxies than expected, not slightly fewer, but almost none at all. The region became known as the Boötes void. It spans roughly 330 million light years in diameter, while containing only around 60 known galaxies. Standard cosmological models predict thousands should occupy a region that large. The absence is so extreme that it changes the texture of the universe itself. The Milky Way stretches approximately 100,000 light years across. You could line up about 3,300 Milky Ways side by side and still not cross the full width of the void. And even that comparison struggles to communicate the scale. If our solar system sat near the center of the Boötes void, the nearest major galaxy in any direction would lie more than 100 million light years away. The night sky would appear almost perfectly black. No glowing band of the Milky Way. No neighboring galaxies. No distant smears of light. Just darkness, stretching outward indefinitely. Human civilization would have developed differently there. Astronomer Greg Aldering once noted that if the Milky Way existed inside the Boötes void, humanity might not have discovered other galaxies until the 1960s. For most of history, we would have assumed the visible universe ended with our own isolated island of stars. Cosmology itself would have formed under completely different assumptions. But the emptiness creates another problem. Modern cosmological models predict voids naturally. Gravity pulls matter into filaments and clusters, leaving lower density regions behind. Yet the Boetes void appears too large and too empty for known processes to have formed it within the current age of the universe. There has simply not been enough time for gravity to evacuate so much matter across such an enormous region. The leading explanation suggests smaller voids gradually merged over billions of years, combining into a larger cavity as matter drifted outward toward denser structures. But the mathematics remain unsettled. Simulations reproduce parts of the process while still struggling to match the full observed scale and depth. And larger voids exist. The Eridanus supervoid extends roughly 1.8 billion light-years across, making it vastly larger overall. But the Boetis void remains uniquely disturbing because of its relative proximity and severe emptiness. It does not feel like a distant, cosmological abstraction. It feels close enough to matter. A place where the universe failed to fill itself in properly, and where darkness exists not because light has faded, but because almost nothing was ever there to begin with. The Milky Way is not stationary. Neither is the local group, the small collection of galaxies containing Andromeda, Triangulum, and dozens of dwarf galaxies surrounding us. Everything in our region of space is moving together through the universe at remarkable speed, drifting toward a location hidden deep in the southern sky. Astronomers first recognized the motion clearly during the late 1970s. They were studying galaxy velocities, measuring how fast nearby galaxies traveled relative to cosmic expansion. Under normal conditions, galaxies should move primarily with the expansion of the universe itself. But the data revealed something additional, a large-scale flow toward the constellation Centaurus at roughly 600 kilometers per second. The movement remained consistent everywhere they looked. Thousands of galaxies shared the same drift, as though an invisible gravitational current was pulling entire galaxy clusters across intergalactic space. The force required immense mass, far more than any visible structure seemed capable of providing. Researchers eventually gave the unseen source a name: the Great Attractor. Estimates suggested the pull originated from a concentration of matter equivalent to tens of thousands of galaxies located around 250 million light-years away. But there was a major complication. The suspected region sat almost directly behind the plane of the Milky Way, inside what astronomers call the zone of avoidance, an area where our galaxy's dust clouds, stars, and gas obscure observation in visible light. We could measure the pull precisely, but we could not see what caused it. For decades, astronomers worked almost entirely through indirect evidence. Galaxies accelerated toward something hidden beyond the dust, allowing researchers to infer mass from motion alone. The situation resembled watching waves move across an ocean while the ship producing them remained concealed behind thick fog. Eventually, other wavelengths began revealing more. Radio telescopes can penetrate galactic dust far more effectively than visible light. Using radio surveys and infrared observations, astronomers identified the Norma cluster as one major source contributing to the observed motion. Norma contains hundreds of galaxies packed together in a dense cluster, hidden almost completely from ordinary optical telescopes. But the story continued expanding outward. In 2016, astronomers identified the Vela supercluster, another enormous structure previously concealed behind the zone of avoidance. Its gravitational influence appeared significant enough to affect large-scale galactic motion across vast distances. More recent studies suggested the flow may extend even further still toward the Shapley supercluster, approximately 650 million light-years away. The Great Attractor may not be a single object at all. It may instead represent multiple layers of gravitational influence stacked along our line of sight, a chain of enormous structures collectively pulling galaxies inward through cosmic space. The motion we detect could be the combined effect of several superclusters distributed across hundreds of millions of light years. And throughout all of this, the motion never stopped. The Milky Way continues traveling toward that hidden region right now at roughly 600 kilometers per second. Earth, the solar system, every ocean, mountain, cloud, and living thing has shared this movement for the entire history of our planet without any direct sensation of it at all. Space itself carries us quietly through the dark. Every direction you look in the sky contains ancient light, not starlight, not galactic light, something older. The cosmic microwave background, usually shortened to the CMB, fills the entire observable universe as a faint thermal glow left behind from roughly 380,000 years after the Big Bang, when space cooled enough for light to travel freely for the first time. It surrounds us constantly. The temperature averages about 2.725 Kelvin, only a few degrees above absolute zero. More remarkable still is its uniformity. Across the sky, temperature variations measure only around 1 part in 100,000. That smoothness helped establish the modern cosmological model by showing the young universe was extraordinarily even on large scales. But one region refused to fit cleanly. In 2004, detailed analysis of CMB maps revealed an enormous patch of sky measurably colder than surrounding regions. The anomaly became known as the cold spot. It stretched across roughly 1.8 billion light years, far too large to dismiss casually as random fluctuation. Statistical analysis suggested the feature required some physical explanation. Astronomers began searching the corresponding region of space itself. In 2015, a team led by Istvan Sapudi identified a massive underdensity aligned with the cold spot. The structure, named the Eridanus supervoid, appeared approximately 20% less dense than surrounding cosmic regions, while spanning around 1.8 billion light-years across. At first, the discovery seemed promising. Photons from the CMB lose and gain energy as they move through gravitational structures. When light enters a void, it gains a small amount of energy falling inward. Under ordinary circumstances, it should lose the same amount climbing back out. But the universe continues expanding during the photon's journey. If the void grows while the light crosses it, the photon exits slightly weaker than it entered. That creates a colder patch. The effect is physically real and expected under relativity, but calculations produced another complication. The Eridanus supervoid alone did not seem capable of generating a temperature difference large enough to explain the full cold spot signal. The anomaly remained colder than the void should reasonably produce, and that gap opened the door to stranger ideas. One published hypothesis suggested the cold spot might represent evidence of a collision between our universe and another universe during cosmic inflation, the brief early period when space expanded exponentially faster than light itself. In some inflationary models, separate universes form like bubbles inside a larger inflating background. If two expanding bubbles touched, the collision could leave a scar imprinted onto the CMB, possibly something resembling the cold spot. This idea entered peer-reviewed scientific literature, not because researchers believed it proven, but because current data does not fully eliminate it. The hypothesis remains speculative. No direct evidence confirms the existence of parallel universes, yet no consensus explanation currently accounts perfectly for the anomaly either. So the cold spot remains suspended between possibilities. Perhaps it is simply an unusually large statistical fluctuation combined with the effects of the Eridanus supervoid. Perhaps the missing explanation lies within ordinary cosmology not yet fully understood. Or perhaps the oldest light in the universe carries a visible imprint from beyond the boundaries of our own cosmic bubble, a mark left before galaxies, stars, or planets ever existed. Not every extreme object in the universe hides in distant galaxies. Some exist inside the Milky Way itself, active and visible within our own cosmic neighborhood. SS 433 is one of them, a binary star system approximately 18,000 light years away in the constellation Aquila, quietly accelerating matter to velocities difficult to comprehend. Two objects orbit each other there. One is an ordinary star, slowly losing material. The other is either a neutron star or a black hole, drawing gas away through gravity. As the stolen matter spirals inward, it forms an accretion disk heated to enormous temperatures by compression and friction. But some of the inflowing gas never reaches the compact object at all. Instead, it is expelled outward. Twin jets erupt from opposite sides of the system at roughly 26% the speed of light, around 78,000 kilometers every second. That velocity alone would carry you from Earth to the Moon in about 5 seconds. Yet the jets continue flowing continuously across interstellar space, and they do not point steadily. SS 433 undergoes precession, a slow, wobbling motion similar to a spinning top, changing orientation as it rotates. The jets complete one full precession cycle every 162.5 days, sweeping through space and carving a giant corkscrew pattern into the surrounding nebula W50. Radio telescopes reveal the structure directly, a visible imprint left by relativistic matter moving through gas clouds over long periods of time. The temperatures remain extraordinary. Jet material reaches tens of millions of degrees, comparable to temperatures inside the core of our sun. Despite this violence, the outflows maintain coherence across several light years before finally dispersing into the surrounding nebula. Magnetic fields help contain and guide the plasma across distances vast enough to span trillions of kilometers. Astronomers eventually classified SS 433 as a microquasar. A quasar is normally powered by a supermassive black hole inside a distant galaxy. A microquasar reproduces the same physical process on smaller scales using stellar mass objects instead. The underlying mechanics remain remarkably similar despite the enormous difference in mass, showing that accretion disks and relativistic jets operate according to the same principles across roughly 10 orders of magnitude. But the system revealed something else as well. In 2019, the High-Altitude Water Cherenkov Observatory, usually shortened to HAWK, detected ultra-high energy gamma rays emerging from regions where SS 433's jets collide with the surrounding nebula. The detection confirmed the system as a pevitron, a natural particle accelerator capable of reaching energies around 1 peta-electron volt. That is 1 quadrillion electron volts. The energy exceeds the capabilities of the Large Hadron Collider at CERN by roughly a factor of 1,000. Human engineering has never produced stable particle acceleration approaching those levels. Yet a compact star system inside our galaxy accomplishes it naturally through gravity, magnetism, and relativistic motion alone. And the implications extend outward from there. Ultra-high energy cosmic rays strike Earth's atmosphere constantly, but their origins remain only partially understood. Many researchers once assumed the most energetic examples required distant extragalactic sources. Systems like SS 433 suggest part of the answer may exist much closer to home, hidden within violent stellar engines already operating silently inside the Milky Way itself. Every second, particles from deep space pass through your body unnoticed. They move through walls, oceans, mountains, and entire planets almost without interruption. Most are harmless at Earth's surface because the atmosphere absorbs them high overhead, converting the incoming particles into cascades of secondary debris before they ever reach the ground. These are cosmic rays. Most cosmic rays are ordinary by astrophysical standards, protons and atomic nuclei accelerated within the Milky Way by supernova remnants, pulsars, and magnetic turbulence. But a tiny fraction belong to a far stranger category. They arrive carrying energies so extreme that even modern astrophysics struggles to explain where they came from. Astronomers classify these as ultra-high energy cosmic rays. Their energies exceed 1 exa-electron volt, meaning 1 quintillion electron volts. The most extreme examples push far beyond even that threshold. On October 15th, 1991, the Fly's Eye detector in Utah recorded the arrival of a particle that became famous almost immediately. Researchers nicknamed it the "Oh my God" particle. The incoming cosmic ray carried roughly 320 quintillion electron volts of energy. The comparison startled physicists. A single subatomic particle, likely a proton, possessed kinetic energy comparable to a professionally thrown baseball. But that energy was compressed into something vastly smaller than an atom, and according to theory, it should barely have survived the journey. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin predicted a natural energy limit for cosmic rays traveling across intergalactic space. The universe itself contains the cosmic microwave background, ancient radiation filling all space. Ultra-energetic particles colliding with those photons should gradually lose energy over long distances. This became known as the GZK limit. Under that model, particles above a certain threshold should not survive journeys longer than roughly 160 million light-years. Yet the Oh my God particle arrived, carrying far more energy than expected. Either its source existed relatively nearby, or some part of the model remained incomplete. But no nearby source fit properly. No known object within the required distance appeared capable of accelerating particles to such extraordinary energies through conventional astrophysical mechanisms. Supernova remnants fall short, pulsars struggle. Even active galactic nuclei face major difficulties explaining the highest observed events cleanly. So, researchers built larger detectors. The Pierre Auger Observatory in Argentina began operations in 2004, spreading instruments across roughly 3,000 square kilometers of open land. Instead of detecting the cosmic rays directly, the observatory measures the giant atmospheric particle showers produced when incoming rays strike molecules high above Earth. Thousands of events have now been recorded. Some statistical patterns suggest weak correlations with active galactic nuclei, the energetic centers of distant galaxies powered by supermassive black holes. But no definitive source has yet been confirmed for the most extreme arrivals. And meanwhile, the particles continue falling silently through the atmosphere. At lower energies, roughly 1 cosmic ray strikes every square meter of Earth each second. Ultra-high energy events remain far rarer, approximately 1 impact per square kilometer each year. Yet even now, while cities sleep and oceans drift beneath the night sky, particles accelerated somewhere in the distant universe are crossing Earth continuously, carrying energies that still resist full explanation. At 5:51 in the morning, Eastern Time, on September 14th, 2015, a faint signal appeared inside a detector in Livingston, Louisiana. It lasted about 2/10 of a second. The pattern rose rapidly in frequency and intensity, then stopped abruptly. For a moment, it looked almost insignificant, but the signal matched a prediction made by Albert Einstein exactly 100 years earlier. Even Einstein doubted such a disturbance could ever be measured directly. The effect seemed too small, too delicate, too deeply buried beneath ordinary vibrations from Earth itself. Yet the signal was real. A second detector in Hanford, Washington, recorded the same pattern 7 milliseconds later. Together, the two instruments confirmed the first direct detection of a gravitational wave, a ripple moving not through space, but through space-time itself. The source existed far beyond the Milky Way. Two black holes, one roughly 29 solar masses and the other 36, had spent billions of years orbiting each other while slowly losing orbital energy. Their separation shrank gradually across cosmic time until the final moments, when they spiraled inward at relativistic speeds and merged roughly 1.3 billion light-years from Earth. Then space-time rang outward from the collision. Gravitational waves differ fundamentally from light, radio waves, or gamma rays. They are not particles or electromagnetic radiation crossing space. They are distortions of space itself, stretching and compressing distances as they pass through the universe. The violence of the merger exceeded ordinary intuition. During the final fraction of a second, the power released in gravitational radiation surpassed the combined electromagnetic output of every visible star in the observable universe for the same duration. Yet no telescope saw the event directly because almost all the energy escaped as geometry rather than light. The merger left behind a final black hole weighing approximately 62 solar masses. The missing mass mattered. 3 solar masses had disappeared completely, converted into pure gravitational wave energy according to Einstein's relation between mass and energy. In that brief instant, more energy was emitted than the Sun will produce across its entire lifetime, and Earth still detected it. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, measures changes in distance using laser beams traveling through vacuum tunnels 4 kilometers long. As the wave crossed Earth, it stretched one arm slightly while compressing the other. The amount changed was almost impossible to imagine. The distortion measured roughly 1,000th the diameter of a proton, yet the instrument resolved it successfully after the wave had traveled for 1.3 billion years across expanding space. Since that first detection, the catalog has grown steadily. As of 2024, scientists have confirmed more than 90 gravitational wave events, including black hole mergers, neutron star collisions, and possible mixed systems involving both neutron stars and black holes. Each detection reveals objects previously invisible to ordinary telescopes, but the deepest shift was conceptual. Before LIGO, gravity was usually experienced as static, the force holding planets in orbit and galaxies together. Gravitational waves revealed something more dynamic. Space itself can vibrate. Entire regions of the universe can flex like fabric under immense stress, and those waves move through everything. Right now, ancient distortions from distant mergers are crossing planets, oceans, stars, and human bodies continuously. Almost all pass unnoticed. But occasionally, somewhere on Earth, an instrument becomes sensitive enough to hear space-time itself briefly changing shape. If you could step far enough away from the Milky Way, beyond nearby galaxies, and beyond local clusters, the universe would stop looking scattered, patterns would begin to emerge. Galaxies would no longer appear randomly distributed through space. Instead, they would arrange themselves into vast interconnected strands separated by immense dark regions. Astronomers call this structure the cosmic web. The idea first emerged during the 1970s through theoretical models of gravity and matter distribution. During the 1980s, large redshift surveys conducted by the Harvard Smithsonian Center for Astrophysics confirmed that galaxies truly do cluster along gigantic filaments extending across unimaginable distances. The universe resembles a network. Galaxy clusters sit at dense intersections where multiple filaments meet. Between them lie enormous voids with relatively little matter, but the filaments themselves are not empty bridges connecting islands of galaxies. They contain enormous reservoirs of material invisible to ordinary optical telescopes. Hot gas drifts there constantly. Temperatures inside these structures reach millions of degrees. Diffuse magnetic fields stretch across hundreds of millions of light years. Dark matter halos, invisible concentrations detectable only through gravity, help shape the framework itself. Modern X-ray observatories eventually revealed that more than half of all ordinary matter in the universe may exist within these vast filaments rather than inside galaxies. For decades, much of it remained hidden. Then astronomers discovered something even stranger. Some cosmic structures appeared too large to exist under current cosmological assumptions. One of the most extreme examples is the Hercules Corona Borealis Great Wall, a colossal concentration of galaxies and galaxy clusters extending roughly 10 billion light years across. The scale becomes difficult to visualize. The observable universe measures about 93 billion light years in diameter. The Hercules Corona Borealis Great Wall spans nearly one-tenth of that distance alone, stretching across a region so large that light itself requires billions of years to cross it. And this creates a theoretical problem. Modern cosmology rests partly on the cosmological principle, the assumption that at sufficiently large scales, the universe should appear statistically uniform in every direction. Small variations are expected. Giant clusters and voids are expected, but structures spanning billions of light years challenge the scale at which uniformity should emerge. Earlier discoveries already hinted at tension. The Sloan Great Wall, identified in 2003 using data from the Sloan Digital Sky Survey, stretches roughly 1.37 billion light years. At the time, many astronomers already considered it uncomfortably large. Then even larger structures appeared in later observations. But the cosmic web continues evolving regardless of human expectations. The voids between filaments also play an active role in shaping cosmic structure. Galaxies near void boundaries experience slight gravitational imbalances because surrounding filament regions contain more matter. Over immense timescales, this causes galaxies to drift outward from emptier regions toward denser walls and intersections. Space subtly rearranges itself. Across billions of years, gravity pulls matter into filaments while emptier regions expand between them. The result is a universe structured less like isolated galaxies floating randomly in darkness and more like an enormous living network stretching across cosmic distances. And somewhere within one thin strand of that network, the Milky Way drifts quietly among countless others, suspended inside a structure vastly larger than the human mind evolved to imagine. Everything you have ever touched belongs to a minority. Every planet, moon, ocean, cloud, human body, and star together account for only a small fraction of the universe's total content. Ordinary matter, the atoms making up all visible structure, contributes roughly 5% of the universe's total energy budget. The remaining 95% is something else. About 27% appears to be dark matter, an invisible form of mass detected only through gravity. It emits no light, absorbs no light, and has never been directly observed interacting with ordinary matter through any force except gravitation. Yet without it, galaxies and galaxy clusters behave in ways current physics cannot explain. The evidence emerged gradually. During the 1970s, astronomers Vera Rubin and Kent Ford carefully measured how spiral galaxies rotate. Under Newtonian gravity, stars farther from a galactic center should orbit more slowly because less visible mass exists beyond them. The outer edges should thin and slow naturally. But that did not happen. Stars near galactic outskirts moved far faster than expected, often orbiting at nearly the same velocity as stars much closer inward. Under ordinary gravity alone, many galaxies should have torn themselves apart long ago. Something unseen was holding them together. Researchers concluded galaxies must sit inside enormous halos of invisible matter extending far beyond their visible stars. The gravitational influence remained measurable even where no detectable light existed. Then stronger evidence arrived from collisions. The Bullet Cluster, located roughly 3.8 billion light years away, consists of two galaxy clusters that passed through one another at enormous speed. Ordinary gas within the clusters interacted electromagnetically and slowed during the collision, heating into bright X-ray emitting clouds visible to telescopes. But most of the mass did not stop. Astronomers mapped gravity there using gravitational lensing, the bending of light by mass predicted under relativity. The strongest gravitational regions appeared separated from the hot gas clouds. Most of the mass had passed straight through the collision unaffected, behaving as though it barely interacted with ordinary matter at all. The observations matched dark matter remarkably well. Scientists proposed several possible particles over the decades. Weakly interacting massive particles, usually shortened to WIMPs, became one leading candidate. Others included axions and sterile neutrinos. Massive underground detectors searched continuously for tiny interactions, while particle colliders attempted to create dark matter directly. Nothing definitive appeared. Alternative ideas also emerged. Modified Newtonian dynamics, called MOND, proposed altering the laws of gravity themselves at extremely low accelerations, rather than adding invisible matter. MOND reproduces some galactic rotation behavior surprisingly well. But larger cosmic structures remain difficult. Galaxy cluster collisions, gravitational lensing patterns, and the evolution of the cosmic web align more naturally with dark matter models than modified gravity alone. So the invisible mass hypothesis remains the dominant explanation despite the absence of direct detection. And meanwhile, the universe continues behaving as though dark matter surrounds us constantly. If dark matter particles exist, enormous numbers are moving through this room right now. Through walls, through the floor, through every living body, through Earth itself. They leave no visible trace and produce no sensation. Yet galaxies rotate because of them. The largest structures in the universe formed because of them. And according to everything modern cosmology currently understands, most of the matter shaping reality is something humanity still cannot identify at all. For most of modern astronomy, scientists assumed gravity would gradually slow the expansion of the universe. Galaxies were moving apart, yes, but the combined pull of all matter should eventually reduce that outward motion over immense stretches of time. That expectation lasted decades. Then, in 1998, two independent research teams studying distant supernovae reached the same disturbing conclusion. Saul Perlmutter's supernova cosmology project and the High Z supernova search team, led by Brian Schmidt and Adam Rias, both discovered that remote galaxies appeared farther away than predicted. The expansion was speeding up. Instead of slowing under gravity, the universe itself was accelerating outward through time. The discovery shocked cosmology because nothing in the standard model predicted such behavior naturally. Researchers needed a name. They called the unknown cause dark energy, a label describing something that appears to make up roughly 68% of the universe's total energy content while remaining completely unidentified. Unlike dark matter, which adds gravitational attraction, dark energy behaves like a large-scale repulsive effect embedded into spacetime itself. And its influence keeps increasing. As the universe expands, ordinary matter spreads thinner. Radiation weakens as wavelengths stretch across larger distances. But observations suggest dark energy maintains nearly constant density even while space grows larger. Over billions of years, that means gravity becomes progressively less important compared to the outward acceleration. The simplest explanation traces back to Albert Einstein. In 1917, Einstein introduced a mathematical term called the cosmological constant into general relativity because he believed the universe was static. Later, when Edwin Hubble demonstrated cosmic expansion, Einstein reportedly abandoned the idea and called it his greatest blunder. But modern observations revived it. Dark energy behaves remarkably similarly to Einstein's discarded constant, though nobody understands why the effect exists physically. The equations reproduce observations successfully while explaining almost nothing about the underlying mechanism. The long-term consequences become increasingly lonely. Within roughly 150 billion years, expansion will push all distant galaxy groups beyond our cosmological horizon, the limit beyond which light can never reach us within finite time. Every galaxy cluster outside the local group will disappear permanently from view. Future skies would darken slowly. Civilizations existing trillions of years from now might see only their local stars and conclude the universe contained nothing beyond them because all evidence of cosmic expansion and distant galaxies would have vanished beyond reach. But some theoretical models become even more severe. One hypothetical version, called phantom energy, assumes acceleration increases without limit. Under that scenario, expansion eventually overcomes gravity itself. Galaxy clusters separate first. Then, galaxies drift apart internally. Later, solar systems lose stability as space expands faster at every scale. The process does not stop there. Eventually, planets, molecules, and even atomic nuclei could be torn apart as space-time expansion overwhelms every known binding force. Cosmologists call this scenario the Big Rip. Current estimates place it roughly 22 billion years in the future if phantom energy proves correct. But regardless of which model survives, one fact remains deeply unsettling. Most of the universe appears controlled by something humanity still cannot identify, while its influence steadily grows across the largest scales of reality itself. The universe expands everywhere at once. Galaxies drift apart because space itself stretches between them, carrying entire clusters outward across cosmic time. Astronomers describe that expansion using the Hubble constant, a measurement telling us how fast distant galaxies recede as their distance increases. For years, the calculation seemed straightforward. Then two different methods began producing two different answers. The first method looks deep into the early universe. Astronomers study the cosmic microwave background, the ancient radiation released roughly 380,000 years after the Big Bang. Then apply the standard cosmological model to predict today's expansion rate. That approach gives a value near 67.4 kilometers per second per megaparsec. The second method stays much closer to home. Researchers directly measure distances to nearby galaxies using Cepheid variable stars and Type Ia supernovae, objects bright and predictable enough to function as cosmic distance markers. That method produces a larger number. Current measurements place it around 73 kilometers per second per megaparsec. The difference may sound small, but at cosmological scales it becomes deeply significant because both methods are extraordinarily precise, and the disagreement refuses to disappear. Astronomers call the discrepancy the Hubble tension. As observations improved, the gap remained statistically strong. The difference has now reached approximately 5 sigma significance, meaning the probability of the mismatch arising through random measurement error is roughly 1 in 3.5 million. In physics, 5 sigma usually means discovery. If both measurement methods are correct, then the standard cosmological model contains an incomplete assumption somewhere within its structure. That possibility unsettles researchers because the model has explained decades of observations remarkably well, from galaxy formation to the evolution of large-scale cosmic structure. But something may still be missing. Some theories propose an early form of dark energy, active only during the universe's first moments. Others suggest previously unknown neutrino behavior or hidden interactions involving dark matter. Some researchers explore modifications to conditions shortly after the Big Bang itself. Each explanation changes fundamental physics in different ways. Another proposal focuses on our location within the universe. The Milky Way appears to reside inside a large underdense region, sometimes called the KBC void. If surrounding space contains less matter than average, local expansion could proceed slightly faster than the broader cosmic rate. That might explain part of the discrepancy, but current estimates suggest it likely cannot explain all of it. The tension remains larger than the void alone appears capable of producing, and the measurements continue improving. New observations from space telescopes, gravitational lensing surveys, and refined supernova catalogs keep narrowing uncertainties while preserving the disagreement itself. Instead of fading with better instruments, the mismatch has become more difficult to ignore. That is what makes the problem so unsettling. The Hubble tension does not resemble an isolated anomaly buried in obscure data. It touches the expansion rate of the universe itself, one of the central quantities underlying modern cosmology. The disagreement sits directly inside the framework scientists use to describe the age, history, composition, and future evolution of reality. And every year, the crack appears slightly wider. Not because observations are becoming less precise, but because they are becoming more precise while still refusing to agree with one another. Most black holes remain tied to something. Stellar mass black holes orbit within galaxies after forming from collapsed stars. Supermassive black holes usually sit deep inside galactic centers, held there by the combined gravity of billions of surrounding stars. But not all of them stay anchored. Under certain conditions, gravitational interactions can eject black holes entirely from their home systems, sending them drifting through intergalactic space alone. Collisions between galaxies, close encounters between multiple black holes, or asymmetric gravitational wave emission during mergers can produce enough momentum to launch them outward at enormous speeds. Once expelled, they become almost impossible to track. In 2023, a research team led by Peter Van Dokkum at Yale identified evidence for a candidate runaway black hole moving through intergalactic space at roughly 1,600 kilometers per second. The suspected object appeared to contain around 20 million solar masses, but astronomers never saw the black hole directly. The evidence emerged through its wake. Hubble Space Telescope images revealed a narrow streak of young stars extending roughly 200,000 light-years behind the invisible object. Researchers interpreted the structure as gas compressed by the black hole's passage through the intergalactic medium, triggering star formation along its path, like the wake trailing behind a ship crossing water. The black hole itself remained dark, and smaller rogue black holes may be vastly more common. Astronomers estimate millions of stellar mass black holes likely drift through the Milky Way alone. Many formed during supernova explosions and later scattered through gravitational interactions over billions of years. Unlike active black holes consuming nearby gas, isolated rogues emit essentially no detectable light. They travel silently. A black hole in complete isolation produces no glow, no visible outline, and no radiation signature obvious to telescopes. In most circumstances, the only way to detect one is through gravity itself. Sometimes, that gravity bends light. When a rogue black hole passes between Earth and a distant star, its gravity can temporarily magnify and distort the background starlight through gravitational microlensing, an effect predicted by general relativity. Astronomers monitor millions of stars searching for those brief distortions, and some candidates have appeared. In 2022, researchers reported what may have been the first isolated stellar mass black hole identified through microlensing alone, located approximately 5,000 light-years away. The object revealed itself only because its gravity subtly altered the appearance of a background star while passing across our line of sight. Otherwise, it would have remained invisible. The statistical implications become uncomfortable very quickly. The Milky Way spans roughly 100,000 light-years and likely contains millions of dark stellar remnants moving independently through that volume. Most cannot be mapped directly because they emit no light and interact with almost nothing unless passing extremely close to another object, which means the galaxy is not empty between stars. It contains wandering gravitational objects that cannot be seen in advance, moving through space without warning or visible signature. Entire paths through the Milky Way pass near black holes humanity would never notice unless one happened to cross directly between us and a distant star. Even then, we would only see the darkness indirectly, revealed for a brief moment by the way it bends light around itself before vanishing again into the larger dark. Every direction you look in the night sky leads backward through time. Light from nearby stars may be years old. Light from distant galaxies may have traveled for billions of years before reaching your eyes. And beyond all of them lies a faint microwave glow filling the entire universe, the oldest light we can observe. But even that light does not reach the beginning. The Big Bang was not an explosion spreading outward through empty space. There was no surrounding void waiting to be filled. Space itself expanded, carrying matter, radiation, and eventually galaxies along with it. Every measurable distance in the universe emerged from an earlier state that was hotter, denser, and compressed beyond ordinary comprehension. Eventually, our equations stop working. The earliest interval modern physics can meaningfully describe is called the Planck epoch, ending roughly 10 to the negative 43 seconds after time zero. That span is known as the Planck time, the smallest meaningful interval current physics allows. Below it, the mathematical frameworks describing reality collapse into contradiction. Temperature during that epoch may have reached approximately 10 to the 32 Kelvin. Density may have exceeded 10 to the 96 kilograms per cubic meter. Under those conditions, general relativity and quantum mechanics produce infinities instead of usable predictions. The equations fail completely. General relativity describes gravity across large scales. Quantum mechanics describes particles and forces at microscopic scales. Both theories work extraordinarily well within their own domains, but inside the earliest universe, both must operate simultaneously, and they cannot currently be reconciled into a single consistent framework. Physics reaches a wall there, but expansion followed almost immediately. During the inflationary epoch, beginning around 10 to the negative 36 seconds after the beginning, the universe expanded at an astonishing rate. Space itself doubled repeatedly every tiny fraction of a second. By roughly 10 to the negative 32 seconds, the universe had expanded by at least a factor of 10 to the 26. This was not ordinary motion. Nothing traveled outward through space faster than light. Instead, space itself expanded, allowing distant regions to separate more rapidly than light could ever move between them. Regions once connected became permanently isolated from one another. That separation still exists. The observable universe is only the portion whose light has had time to reach us since the beginning of cosmic expansion. Beyond it may lie vastly larger regions, forever unreachable, cut off not by technology or distance alone, but by the geometry of space-time itself. And inside that violent expansion, something tiny became everything. Quantum fluctuations, microscopic variations in energy density occurring at subatomic scales, were stretched outward during inflation until they spanned entire galaxies. Slightly denser regions accumulated more matter over billions of years. Those imbalances eventually formed stars, galaxy clusters, filaments, and cosmic voids. The largest structures in existence began as quantum randomness, but what existed before the Big Bang remains unresolved. Some physicists argue the question itself may be meaningless if time emerged alongside the universe rather than preceding it. Under the Hartle-Hawking no-boundary proposal, asking what happened before the Big Bang resembles asking what lies south of the South Pole. The direction itself may not exist. Long before galaxies filled the sky, the universe drifted through an age with nothing visible in it. No stars burned, no planets reflected light, no nebulae glowed across interstellar space. After the release of the cosmic microwave background, roughly 380,000 years after the Big Bang, the universe entered a period that remained lightless for hundreds of millions of years. This was the cosmic dark ages. Darkness here did not mean shadow. Shadows require nearby light sources. During this era, visible light itself did not yet exist anywhere in the universe. There were photons from the ancient microwave background, stretched into low-energy wavelengths by cosmic expansion, but nothing producing visible illumination. The universe had become transparent, but it had not yet become luminous. Hydrogen and helium filled nearly all of space. These were the simplest elements possible, formed during the first minutes after the Big Bang, while temperatures remained unimaginably high. Gravity slowly began pulling this gas into denser regions, creating invisible structures extending across enormous distances. Filaments formed first. Dark matter halos, massive concentrations of invisible matter inferred through gravity alone, acted as scaffolding around which ordinary gas accumulated. Over immense spans of time, hydrogen clouds cooled and condensed inside these gravitational wells. Nothing moved quickly. The universe during the Dark Ages was remarkably quiet, compared with later cosmic history. No supernovae exploded. No quasars blazed from galactic centers. Space contained enormous reservoirs of gas, gradually collapsing inward under gravity, still waiting for temperatures and pressures high enough to ignite fusion. But eventually, somewhere inside those collapsing clouds, the first stars formed. Astronomers call them population, three stars, the earliest generation of stellar objects ever to exist. They were fundamentally different from stars born later because the universe then contained no heavy elements at all. No carbon, no oxygen, no silicon, no iron. Only primordial matter remained. Modern stars contain traces of earlier stellar generations mixed into their gas. Population 3 stars did not. They formed entirely from pristine hydrogen and helium left behind by the Big Bang itself. Current models suggest many of these stars became extraordinarily massive, perhaps exceeding hundreds of solar masses. Without heavier elements to cool, collapsing gas efficiently, the clouds produce stars far larger and hotter than most stars forming today. They burned violently. A massive star exhausts its fuel rapidly because fusion rates increase dramatically with temperature. Many population 3 stars may have survived only a few million years before collapsing or exploding as supernovae, creating the first heavy elements ever forged inside stars. Every carbon atom in your body traces back to processes that began there, but no confirmed population 3 star has ever been directly observed. They vanished billions of years ago, leaving only indirect evidence behind. In 2024, the James Webb Space Telescope identified spectroscopic signatures, meaning patterns in light revealing chemical composition, that may indicate population. 3 stellar populations inside the distant galaxy, GSNDG 9422. We see that galaxy as it existed nearly 13 billion years ago. As more early stars ignited, their radiation transformed the universe itself. Ultraviolet light stripped electrons from surrounding hydrogen atoms, gradually clearing the dense hydrogen fog that had filled intergalactic space since shortly after the beginning. The cosmic dark ages ended slowly, not with a single dawn, but with countless first lights appearing across an expanding universe. Every horizon in daily life marks a limit created by distance. The horizon at sea exists because Earth curves away beneath you. The horizon in space exists for a different reason entirely. It is created by time. The observable universe is not the entire universe. It is the portion whose light has had enough time to reach us since cosmic expansion began. Measured from Earth in every direction, that observable boundary lies approximately 46.5 billion light-years away. Earth is not central to the universe. Any observer anywhere would see themselves at the center of their own observable sphere because light travels at a finite speed. We occupy the center only from our perspective, the way every observer necessarily does. But eventually, observation stops. The oldest light we can detect is the cosmic microwave background, released roughly 380,000 years after the Big Bang. Before that era, the universe remained opaque. Free electrons scattered photons constantly, preventing light from traveling meaningful distances. Space was filled with fog then. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, photons finally began moving freely across space. Those ancient photons still travel today, stretched into microwave wavelengths by cosmic expansion. The cosmic microwave background forms a wall around observable reality. Beyond it, the universe almost certainly continues. Galaxies likely exist there, So do stars, black holes, and cosmic structures extending far outside our visible horizon. The extraordinary uniformity of the microwave background suggests the larger universe beyond our observational limit resembles the region we can see. But resemblance does not mean connection. Because space itself expands, distant galaxies move away from us even while remaining locally stationary within their own regions of space. At approximately 14 billion light years, recession velocity reaches the speed of light itself. Galaxies farther away than that have crossed a boundary called the cosmological horizon. Light emitted from them today will never arrive here. We may still observe older light emitted billions of years ago, before those galaxies crossed beyond causal contact, but anything happening there now is permanently unreachable. No future telescope, no spacecraft, no signal could ever bridge that growing separation. The universe becomes inaccessible long before it ends. Inflationary cosmology suggests the total universe may extend vastly beyond the observable sphere. Some models propose space is effectively infinite. An infinite universe carries consequences difficult for the human mind to hold comfortably. Matter can arrange itself only in finite ways. If space continues forever, then every physically possible arrangement of atoms should eventually repeat somewhere, not approximately, exactly, another Earth, another Milky Way, another version of this exact moment occurring unimaginably far beyond the observable boundary. But no evidence from those regions can ever reach us. This limitation shapes modern cosmology in unsettling ways. Some physicists invoke the anthropic principle, the idea that physical constants appear finely tuned for life because only universes permitting observers can ever be observed. Others reject that reasoning entirely, arguing it explains nothing fundamental. The debate remains unresolved. Every photon from the cosmic microwave background reaching Earth tonight has traveled uninterrupted for 13.8 billion years. Those photons departed when stars had not yet formed and galaxies did not yet exist. When we observe them, we are not simply looking far away. We are looking directly against the boundary of the knowable universe itself. One day, every star you have ever seen will disappear. Not suddenly, not through catastrophe. The universe is moving toward darkness through exhaustion, a slow draining of usable energy stretched across spans of time so enormous that human history vanishes into insignificance beside them. The sun still contains roughly 5 billion years of hydrogen fuel. After that, it will swell into a red giant before collapsing into a white dwarf, a dense stellar remnant no larger than Earth. But the sun is not among the longest-lived stars. Small stars survive far longer. Red dwarfs, containing only around 8% of the sun's mass, burn their fuel so slowly they may continue shining for up to 10 trillion years. That is roughly 700 times longer than the current age of the universe. They will be the final stars. Eventually, around 10 to the 13 years after the beginning, even the last red dwarf will exhaust its remaining hydrogen. By then, nearly all cold interstellar gas, suitable for forming new stars, will already have been consumed or scattered. No fresh stars will ignite again. For the first time since the cosmic dark ages, the universe will contain no visible stellar light. Galaxies will remain structurally intact for a while longer, but they will drift through space, populated only by remnants. This future period is called the degenerate era. White dwarfs will cool gradually toward absolute zero, the lowest possible temperature allowed by physics. Neutron stars will persist as collapsed atomic cores suspended in expanding darkness. Black holes will continue orbiting silently through increasingly empty galaxies. Time stretches strangely there. A white dwarf becomes what astronomers call a black dwarf only after cooling for approximately 10 to the 15 years. A black dwarf is a cold crystalline sphere composed mostly of carbon and oxygen, no longer glowing at any wavelength visible to human eyes. None exist yet. The universe itself remains far too young. Even the oldest white dwarfs have not had enough time to cool completely. Every black dwarf belongs to the future alone. But matter itself may not survive forever. Many grand unified theories, frameworks attempting to merge fundamental forces into one description, predict proton decay. A proton, one of the particles forming atomic nuclei, may eventually disintegrate into lighter particles over timescales around 10 to the 34 years. This has never been observed directly. But if proton decay occurs, every remaining structure made of ordinary matter will slowly dissolve. Planets will disintegrate atom by atom. Black dwarfs will evaporate into radiation. Even neutron stars may eventually decay into diffuse streams of elementary particles. After that, only black holes remain. But black holes are not eternal either. Through Hawking radiation, a quantum mechanical process proposed by Stephen Hawking in 1974, black holes slowly emit thermal radiation and lose mass over unimaginable spans of time. Large black holes evaporate extraordinarily slowly. The most massive black holes, containing billions or trillions of solar masses, may survive until roughly 10 to the 100 years from now, a Google years. Their final moments release brief bursts of radiation into a universe otherwise almost completely empty. Then structure ends. No stars, no planets, no galaxies, only thin radiation spreading through expanding spacetime, growing colder and more dilute forever. A fire only burns because heat flows outward. Stars shine because their cores remain hotter than the surrounding vacuum. Galaxies evolve because gravity pulls matter into denser arrangements. Life exists because energy moves continuously from one state into another. Every process depends on imbalance. The second law of thermodynamics states that entropy, a measure of disorder and energy dispersal, can only increase or remain constant inside a closed system. Order breaks down more easily than it forms. Heat spreads outward. Concentrated energy becomes diffuse. The universe follows this law everywhere. Since the first moments after the Big Bang, entropy has been increasing continuously. Stars temporarily reverse local disorder by fusing atoms into heavier elements, but they do so by releasing vastly larger amounts of heat and radiation into surrounding space. The total entropy still rises. Heat death is the name given to the final state produced by this process. It is not an explosion or collapse. It is the gradual elimination of every usable energy difference in existence. Eventually, temperature becomes uniform everywhere. Without hotter regions and colder regions, no work can occur. Chemical reactions stop. Fusion ends. Gravity can no longer build new structures efficiently because matter becomes too diffuse across expanding space. Motion continues, but meaningful processes cease. The universe survives physically, but activity ends. After the last black hole evaporates through Hawking radiation around 10 to the 100 years after the Big Bang, the cosmos enters an era beyond ordinary comprehension. For comparison, the universe today is only around 10 to the 10 years old. The gap between now and heat death exceeds the gap between the Big Bang and today by 90 orders of magnitude. During that immense future, galaxies disappear beyond cosmological horizons. Stellar remnants decay. Black holes evaporate one by one into low energy radiation. Eventually, only extremely dilute particles remain drifting through nearly empty spacetime. Darkness becomes permanent there. But complete stillness may never truly arrive. Quantum mechanics allows tiny fluctuations to occur even inside vacuum states. Virtual particles briefly emerge and vanish continuously at microscopic scales. Under normal conditions, these fluctuations remain insignificant. Given infinite time, however, even extraordinarily improbable events become statistically possible. This leads to one of the strangest ideas in modern cosmology. A Boltzmann brain is a hypothetical self-aware entity assembled spontaneously through random quantum fluctuations inside a high-entropy universe. The probability is unimaginably small, but an infinite future provides unimaginable opportunity. A conscious mind could appear briefly, complete with false memories of planets, stars, history, and identity, before dissolving back into randomness moments later. Some physicists argue this creates a genuine paradox. If heat death lasts forever, and random conscious observers can occasionally fluctuate into existence, then statistically such observers might vastly outnumber naturally evolved minds like ours. That possibility forces uncomfortable questions about observation, probability, and the nature of reality itself. No consensus exists, but the larger direction remains clear. Every galaxy collision, every neutron star merger, every black hole, every living world, every structure in the observable universe exists inside a cosmos already moving toward thermodynamic equilibrium. Entropy increases quietly beneath every event we have explored. The final destination is not violence, it is exhaustion. Long before Earth existed, matter was already being recycled through dead stars. Hydrogen emerged first, formed when the universe cooled enough for protons and electrons to combine roughly 380,000 years after the Big Bang. For hundreds of millions of years, hydrogen and helium drifted through darkness until gravity compressed the first stars into existence. Inside those stars, something new began. Nuclear fusion forced lighter atoms together under enormous pressure and temperature. Hydrogen fused into helium, helium fused into carbon, carbon fused into oxygen, neon, silicon, and heavier elements as stellar cores grew hotter and denser across millions of years. The oxygen entering your lungs tonight was forged there. The calcium inside human bones formed in stellar interiors that no longer exist. The iron carried through human blood was assembled inside massive stars whose cores eventually collapsed and detonated as supernovae long before the solar system formed. Those explosions scattered enriched matter across interstellar space. Shockwaves from supernovae compressed nearby gas clouds, mixing newly formed heavy elements into vast molecular nebulae. Over immense stretches of time, gravity gathered portions of that material into new stars and planets. Our solar system emerged from one such cloud around 4.6 billion years ago, but certain elements required even more violent origins. Gold, platinum, uranium, and many of the heaviest naturally occurring elements are now believed to form primarily during neutron star mergers. When two neutron stars collide, densities and temperatures become so extreme that atomic nuclei capture neutrons faster than radioactive decay can occur. This process lasts only seconds. Yet, during those seconds, enough heavy elements can be created to outweigh entire planets. The debris expands outward through space, eventually mixing into future generations of stars, asteroids, oceans, and living organisms. Any gold ring nearby likely began in such a collision. Even carbon itself depends on an extraordinary coincidence deep inside stellar physics. Carbon forms through the triple alpha process, where three helium nuclei combine inside red giant stars. The reaction is so statistically unlikely that physicist Fred Hoyle predicted carbon 12 must possess a specific resonant energy state, allowing the process to proceed efficiently. Later experiments confirmed the resonance exactly where Hoyle predicted. Without it, complex chemistry would barely exist. Every atom in every human body, therefore, carries a history older than Earth itself. Hydrogen atoms inside living cells may once have drifted through primordial gas clouds near the beginning of cosmic time. Carbon atoms inside neurons may have circulated through multiple extinct stars before arriving here. The atoms endure, configurations change. Bodies form temporary arrangements from ancient matter, maintaining structure briefly before dispersing again into wider cosmic cycles. Nothing material in this room was created recently in any absolute sense. It was reorganized, but that changes the scale of human existence entirely. The magnetars, black holes, neutron star mergers, and collapsing stars explored throughout this journey are not distant curiosities disconnected from ordinary life. They are the manufacturing chain behind every solid object, every breath, every living tissue, and every conscious mind listening now. The terrifying places built us first. Across the observable universe, stars have been turning on for billions of years, longer than the sun has existed. Many of those stars formed planetary systems. We now know planets are not rare accidents. Observations from Kepler, TESS, and ground-based surveys suggest the Milky Way alone may contain hundreds of billions of planets, including billions orbiting within regions where liquid water could potentially exist. The chemistry required for life appears everywhere. Carbon drifts through molecular clouds. Water vapor surrounds, forming stars. Organic molecules have been identified inside meteorites, comets, and interstellar gas. Nothing about Earth's raw ingredients appears unique, but the sky remains silent. In 1950, during a lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi asked a deceptively simple question. If intelligent civilizations should be common across cosmic time and distance, where is everybody? The numbers create the paradox. The universe is approximately 13.8 billion years old. The Milky Way formed more than 13 billion years ago. Some stars within it are billions of years older than the Sun. Even a civilization traveling far below light speed could gradually spread across the galaxy through self-sustaining colonies within tens of millions of years. Cosmically, that is almost nothing. A civilization, advancing slowly, pausing for thousands of years between journeys, could still occupy the entire Milky Way long before humanity evolved its first mammals. Yet we see no probes, no engineered structures, no radio transmissions confirmed as artificial, and no visible alteration of nearby stars or galaxies. Not even ruins. But absence of evidence is difficult to interpret. Space is vast beyond intuition, and human technology has searched only a tiny fraction of it. Modern radio astronomy has examined a narrow range of frequencies for an extremely brief moment in cosmic history. We may simply be early. Another possibility is more unsettling. In 1998, economist and philosopher Robin Hanson proposed the concept of the Great Filter. Somewhere between dead chemistry and galaxy-spanning civilization lies a barrier so difficult that almost nothing passes through it. The location matters enormously. If the filter lies behind us, then some earlier transition was extraordinarily improbable. Perhaps simple cells rarely form. Perhaps complex cells almost never emerge. Perhaps multicellular life usually fails before intelligence appears. If so, humanity may already represent a staggeringly unlikely outcome. But if the filter lies ahead, the silence changes meaning entirely. Technological species may repeatedly emerge, advance briefly, then disappear through environmental collapse, warfare, artificial intelligence, resource exhaustion, or dangers not yet recognized. Civilizations would flicker briefly across cosmic time, then vanish before spreading far enough to become visible. There are softer explanations. Advanced civilizations may lose interest in expansion. They may communicate in ways humans cannot detect. They may remain hidden deliberately. The universe may contain intelligence everywhere, separated by distance and time so immense that overlap never occurs. We do not know. But after everything explored in this journey, the silence itself becomes one more terrifying place, stretching between galaxies, waiting without explanation. For almost the entire history of the universe, there was nobody here to witness it. Stars formed and died unseen. Galaxies collided in silence. Black holes merged beyond observation. The cosmic microwave background crossed expanding space for billions of years before any living system evolved capable of detecting it. Then, very recently, something changed. Matter on one small planet began asking questions about the larger structure surrounding it. Human beings learned to grind glass into lenses. Telescopes appeared. Mathematics expanded outward alongside observation, and the universe slowly became measurable. The timescale is astonishingly short. Anatomically, modern humans have existed for roughly 300,000 years. Written language emerged around 5,000 years ago. The telescope has existed for only about 4 centuries. Edwin Hubble confirmed the existence of galaxies beyond the Milky Way less than 100 years ago. Before that, the entire observable universe appeared much smaller. The expansion of space itself was discovered within living memory of the Wright brothers' first flight. Pulsars were identified in 1967. The cosmic microwave background was discovered accidentally in 1965 by Arno Penzias and Robert Wilson while troubleshooting radio interference. Gravitational waves were first directly detected in 2015. That signal traveled 1.3 billion years across space before reaching Earth. For nearly all of that journey, no organism existed capable of understanding what it was. Then, during a tiny interval in cosmic history, detectors built by humans measured a distortion smaller than a proton's width and recognized it as the collision of black holes. The universe became self-aware of one of its own processes. But the same pattern repeats across everything explored here. The Botez void remained unknown for hundreds of millions of years, despite occupying a region larger than thousands of galaxies. TON 618 burned with the brightness of trillions of suns long before Earth formed, yet only recently received a catalog designation from human observers. Even the oldest light in existence waited for us. The photons of the cosmic microwave background traveled uninterrupted for 13.8 billion years before striking detectors carried above Earth's atmosphere. The moment of detection was not merely a human event. It altered the universe permanently. For the first time, matter inside the universe understood something about its own origin. That is historically unusual on a cosmic scale. But knowledge arrives unevenly. The Hubble Space Telescope launched in 1990, The James Webb Space Telescope began scientific operations in 2022. Entire categories of cosmic structure remained invisible until the instruments capable of detecting infrared light, X rays, radio waves, or gravitational waves finally existed. We are still at the beginning. Many of the discoveries shaping modern cosmology are younger than the people listening to this now. Some of the terrifying places in this journey were completely unknown a single generation ago. And after 13.8 billion years of darkness, collapse, expansion, and silence, you exist during the brief moment when the universe has begun explaining itself to itself. A photon crossing the void travels for 330 million years without encountering a galaxy. That distance is difficult to hold in human thought. When light beginning that journey left the far side of the void, Earth did not yet contain dinosaurs. Continents occupied different positions. Mammals had not evolved. Entire geological eras still waited ahead. Yet the photon continued uninterrupted. The universe operates comfortably on scales that erase ordinary history. A gamma ray released 13.1 billion years ago by a collapsing star traveled through nearly the entire age of the cosmos before reaching a detector orbiting Earth in the 21st century. During its journey, galaxies assembled around it. The Milky Way formed. The solar system condensed from interstellar gas. Oceans appeared on Earth. Life emerged, diversified, survived extinctions, and eventually developed technology capable of recognizing where that photon came from. Only then did the journey acquire meaning. But even nearby cosmic events unfold across distances that overwhelm intuition. The magnetar flare of December 27, 2004, originated 50,000 light-years away on the opposite side of the Milky Way. The burst crossed the galaxy, entered Earth's atmosphere, and altered the ionosphere measurably despite traveling farther than human civilization has existed. The event itself lasted fractions of a second. The gravitational waves detected by LIGO in 2015 carried an even older story. Two black holes spiraled toward each other for billions of years before merging 1.3 billion light-years away. The distortion passed silently through galaxies, stars, planets, and living organisms before instruments sensitive enough finally measured it. Space became archaeology. Every distant observation shows the universe at an earlier stage because light requires time to travel. Looking outward means looking backward. The Andromeda Galaxy appears as it existed 2.5 million years ago. TON 618 appears as it existed when the universe itself was young. Its present state is unknowable for now. This creates a strange relationship between knowledge and absence. Astronomers never observe the universe directly as it exists in the current moment. They reconstruct it from delayed signals arriving across immense distances and timescales. Every telescope, therefore, becomes a machine for studying vanished conditions. But the terrifying places explored throughout this journey are not immediate threats. No known magnetar lies close enough to sterilize Earth. No gamma-ray burst is currently aimed at us from lethal range. Dark energy unfolds across spans of time far exceeding human civilization. The danger is not practical. It is contextual. Human intuition evolved for distances measured in footsteps and lifetimes measured in decades. The brain that once tracked movement through grasslands now attempts to comprehend black holes larger than solar systems, invisible matter outweighing galaxies, and light traveling for billions of years through expanding space. The scale resists instinct completely. Yet this violent, ancient, incomprehensibly large universe is not separate from us. It is the actual environment surrounding every human life, every memory, every ordinary moment quietly unfolding beneath the night sky. The universe is slowly exhausting itself. Stars convert hydrogen into heavier elements and radiate the energy away into space. Galaxies drift farther apart as expansion accelerates. Black holes absorb matter, then over unimaginable timescales, lose mass through Hawking radiation, the quantum process by which empty space near an event horizon produces escaping particles. Nothing replenishes what is spent. This decline began at the beginning. The Big Bang was not chaos in the ordinary sense. It was an extraordinarily ordered state, dense with usable energy and low in entropy. Entropy meaning the number of ways matter and energy can be arranged. Since then, entropy has increased continuously as the universe expanded and structure dispersed. Everything moves in that direction. But inside this long thermodynamic decline, matter briefly began organizing itself into extraordinary complexity. Gravity formed stars. Stars forged heavy elements. Chemistry emerged on at least one planet. Molecules assembled into living systems, and eventually one species developed nervous systems capable of modeling reality beyond immediate survival. That development was not inevitable. The human brain contains roughly 86 billion neurons linked through approximately 100 trillion synaptic connections. Within that fragile structure exists the ability to imagine distances larger than galaxies, to detect radiation from dead stars, and to reconstruct events that occurred billions of years before Earth formed. Matter learned to examine itself, but the universe itself does not recognize any of this. A black hole merger produces gravitational waves whether or not anyone measures them. A gamma ray burst crosses intergalactic space without awareness of the planets it passes. The Boötes void remained empty long before humans existed and would remain empty if humanity disappeared tomorrow. Meaning is not built into the cosmos automatically. It appears here instead, inside conscious systems capable of assigning significance to otherwise indifferent events. The terrifying places explored throughout this journey have no emotional weight on their own. A magnetar does not know it is dangerous. Ton 618 does not know it is vast. The interpretation exists within minds. That changes the scale of consciousness entirely. For billions of years, stars exploded without witnesses, galaxies formed without observers. Then, during a remarkably narrow interval of cosmic history, living organisms emerged that could map the cosmic microwave background, detect gravitational waves, and calculate the future death of the universe itself. Knowledge became physically real. Right now, in this brief window before the stars disappear and before expansion carries galaxies permanently apart, the universe contains beings capable of understanding where they are. That window may be exceptionally short relative to cosmic time, but it exists now. The terrifying places in this journey will outlast humanity by unimaginable spans. Most already existed before Earth formed. Yet tonight, across one small planet, orbiting one ordinary star, they are being contemplated consciously. Not merely existing, known